Good morning. Today we'll be discussing the problem of shoulder implant X-ray manufacturer classification. So what is this problem? This problem, in fact, is related to shoulder injuries, where there are some specific shoulder injuries that require an operation where a prosthetic joint is installed in the place of the shoulder, such as, for example, this image shown right here, where this iron frame represents a prosthetic joint. A novel data set was introduced in 2020 specifically for this problem, and this data set is available on the UCI machine learning repository. In fact, the purpose of this data set is not to classify the presence or the unpresence of a prosthetic joint, but the purpose of this data set is to classify the manufacturer of the prosthetic joint. So how can that be used? It can be used in the process of replacing or repairing the prosthetic joint. So the information of knowing who was the manufacturer is a valuable piece of information. So this data set right here, they collected 597 instances or X-ray scans, and the images belonged to 4 classes that represented 4 manufacturers. These manufacturers are called Zimmer, Tornier, DuPuy, and Coldfield, as shown here in this image and paper. So what did this guy who originally proposed this approach do? Well, he used a lot of machine learning and deep learning techniques to solve the problem. And there were other people who used the same data set to try to solve the problem. The best accuracy that this guy reached was 85%. No, I'm sorry, it was 80.4% using a network called NASNet. And then following that development, another paper published their own architecture, deep learning architecture to solve the same problem, and they reached an accuracy of 85.92%. And the last deep learning paper that published their work reached an accuracy of 97.2%. using their architecture, which used something called the channel selection layer. Also, some people used YOLO version 3 for the object detection of the place of the joint. However, their dataset was not published, so we cannot go forward with this mechanism. It's important to note that there are other machine learning techniques that were used, traditional machine learning techniques that are not related to deep learning, such as those methods that are listed right here. In addition to the machine learning methods that were used by the guy who published the paper himself. So the guy who made the dataset himself or herself. So the people who made the dataset benchmarked the dataset using multiple machine learning techniques. The best one of them was the random forest classifier. And the random forest classifier, when they used it, it got an accuracy of 56%. Before going on into what I did, I'd like to discuss some other finding that I found in the literature, which is related to X-ray semantic segmentation. So a particular work called XNet, which represents a network for semantic segmentation that is made specifically for X-rays. This network was made specifically for the semantic segmentation of X-rays. So how can we benefit from that? We can use that semantic segmentation to give us this yellow filter over the prosthetic joint, because normally the only area we're interested in is this yellow labeled area right here. For example, in the images down here in the dataset, we're only interested in the area of the prosthetic joint itself for the classification. We're not interested in this black frame of the X-ray, and we're not interested in the bones or any random printing on the paper itself, of the X-ray itself, such as this one. We're only interested in the prosthetic joint itself, which is mostly contained in the yellow area and the mask of the semantic segmentation. So it would be really helpful to use this mask. However, the guy who published this paper and used XNet didn't publish the weights, and he also did not publish the dataset that was used for the training. So this method is not feasible going forward. So my research methodology basically is that I thought that why should we use deep learning? You know, deep learning almost reached the saturation at 97.2% accuracy. So I thought that it is more reasonable to target pure machine learning and pure non-deep learning methods to try to improve the accuracies and push them up a little bit. What I did was augmenting the data set, and then I used the principal component analysis for dimensionality reduction, and then I used the random forest with the augmented data, and I used the random forest classifier with the data processed with the PCA, and I used the gradient boosted classifier with the PCA data, and I used the SVM with the PCA data. So taking a look at the code, we are just here loading the data, labeling the data, and all this stuff. Then right here, this is the augmentation part of the data. So we rotate an image, we translate an image, perform shear, scaling, cropping, horizontal and vertical flipping, and the addition of Gaussian noise. And as you can see right here, these are the these are the augmented pictures from the dataset. So this is the pre-processing step of the dataset. So after we do that, we first perform the random forest with non-augmented data and without PCA, because this is the baseline that was discussed in the original work by Urban and his colleagues. Urban was the name of the scientist or the researcher who made the dataset. So he's the first guy who benchmarked the dataset. So the reason we're performing this is to use this as a comparison for ourselves through this work to know if we're walking down the right path. So we performed random forest with non-augmented data, then and without PCA, and then before going into the machine learning methods that we used, I just wanted to let you know that when we performed the PCA to keep 95% of the variance in the data, the dimensionality was reduced from this number only to 36 to keep 95% of the variance in the data. And I think that this is something really important, because dimensionality reduction is crucial when we are considering a classification task, because it helps to reduce the complexity of the problem. Also, an important note to mention is that we only used 100 images out of the dataset as testing images, which means that 16.75% of data was used as testing data. Also, all the images were reshaped to do 256 and 3 channels, even though it's grayscale. So now, returning to the traditional machine learning methods that we used the random forest with the non-augmented data and without PCA as the baseline. And this was the method that was used by Urban and his colleagues. Then we performed the same random forest without PCA, but with the augmented data. Then we performed the same random forest with PCA, but without using the augmented data because the augmented data caused a problem with Google Colab. And then we performed the gradient boosting with the PCA and also not using the augmented data. And then we performed SVM and XGBoost with PCA and using the non-augmented data. So as it can be seen here from the results, the highest accuracy, of course, is for experiment 2, which used the augmented data, and it got an accuracy of 56%. So just for reference, these are the numbers, these are the names of the experiments, and these are their numbers. So this table is corresponding to this list of experiments. So here, experiment 2, we find that the accuracy is 56%, which is the random forest classification with the augmented data. And the first one was the method implemented by Urban without the data augmentation. So we can see a jump of 3% in the accuracy. Also, we can see that when we use the PCA, the drop in the accuracy isn't really that large. The drop in the accuracy is really small. And since the drop in the accuracy is really small, I said, so why not perform the PCA with the remaining methods that I wanted to make? So why not use the data after performing the PCA with the gradient boosted classification, the SVM classification, and the XGBoost classification? So when I performed those experiments with the PCA, the accuracy of the SVM classifier was fairly good. It was 51%. However, the accuracies of the XGBoost and the gradient boosted classifier were bad to some extent. Also, it is really important to note here that this is one of the examples of the confusion matrices, and this is the specific confusion matrix from experiment 3. So let me get down here to experiment 3. So this is its confusion matrix. I hope I'm in the right place. Okay, yeah, this is the confusion matrix. So as we can see, most of the data is classified as class 2. So this is really because the number of data points in class 2 is higher than most of the other classes. So for example, this is a histogram of the classes in our data. As you can see, class 2 is really overwhelming all of the data. So this is a problem in the data set. How can it be solved? We can really just augment the other classes more than this class. That would be one of the solutions that can work. So in conclusion, the random forest classifier was the best one. And going forward, if we want to use lightweight models, we can use MobileNet because it's a really small model that can be deployed on edge devices. And also if the researchers who did the work of XNet publish the weights or their data set in the future, it would be really great to try semantic segmentation on the X-ray image and having a mask that only takes the bones or and the prosthetic joint as an input to the model to make the classification problem easy. Thank you for listening, and if you have any questions, please do not hesitate to contact me.